What's happening, folks? Geologist Philip Prince going to talk about flash floods today. It's been a big thing in the news this summer throughout the country. Most recently, of course, here in Kerr County, Texas, and downstream on the Guadalupe River. Uh, Believe it or not, just looking at the landscape that you see right now, from a geologic perspective, if you see a landscape that looks like this one, you sort of automatically know that it's prone to extreme flash flooding. I've heard about the Guadalupe River rising 25 feet or something like that in just a matter of hours, literally sort of walls of water coming down the river channel. That sort of thing does happen, but it does require certain background characteristics. I'm actually going to compare this to what happened up in West Virginia earlier this summer, and also what happened in Eastern Kentucky back in 2022, because all of these landscapes, like the one you see here, have sort of a common characteristic. And in particular, I think I'm drawing here the South Fork of the Guadalupe. So the river there is moving into a wider valley once you get down towards Comfort and places like that. But the areas of the landscape that are feeding that river water, so all of these little feeder streams, tributaries coming in, if you really look close, they branch and then they go up here and branch again and again and again. So it becomes a really sort of intensely carved up landscape. And the term for that geologically is high drainage density. And high drainage density landscapes like this one are notoriously prone to really, really fast flood responses. So they're prone to producing what we would call flash type flooding. If you put the amount of rain that this landscape received on any landscape, you're talking 12 inches, 15 inches, something like that, in just a few hours overnight. You're gonna have a flood problem, but it's the rate of that flooding. How fast does it happen? Where are you? Can you recognize that it's happening, and can you have a safe escape route? Speed is really the question. And as we zoom in closer here, as you're seeing a landscape like this, it's actually really sort of almost kind of wrinkled and complex looking when you get close to it. A landscape like this takes precipitation and puts it in channels and runs it into bigger channels very, very quickly. Now, in the particular case of this part of Texas, uh, they were in a drought here, I believe, prior to the event, and the ground surface was sort of hard and baked. So the rainfall that went onto it ran off even faster. And again, as a geologist, if you see a place like this, what's on your mind is actually a number of things we'll take a look at here. But one is the very rapid response of it to rainfall. Now, what produces a landscape like this, it tends to be like flat lying layers of rock. And we got this pulled up here on the national map. We're looking here at LiDAR imagery just south of Hunt, Texas. And if we zoom in here, you can actually see these rock layers poking out here on the hillsides and very, very closely spaced stream channels there, all of which are funneling water into bigger streams, which go down here into the South Fork of the Guadalupe River. What you're seeing there with the LiDAR imagery, which is kind of these parallel lines, sort of individual rock layers, it looks like they're pretty thin. If you were standing there and walking up that hill, you would be crossing a lot of thin layers. And frequently, having thin layers or having rock that can come apart into small pieces is one geologic factor that goes into producing this really, really high drainage density. And also having the layers being essentially flat lying so that there's not any particular directionality to the river systems. They sort of spread equally in all directions. That's another factor that tends to produce the very high drainage density effect that you have in the landscape here that's so good at putting water into streams very quickly. We'll see if we can get the 3D viewer to load up here on the national map. Sort of an exciting detail about the National Map Service here from the U.S. Geological Survey is that as of very recently, you can actually access this 3D LiDAR data for much of the country, and it's a very valuable resource if you're just interested in looking at sort of the details of the landscape or what the landscape looks like. And what you're seeing right here is a landscape that is going to be prone to producing stream networks like this and with stream networks like that in a hot climate that can dry the land surface. It's going to be an absolute flash flood making machine. So when it comes to the idea of this happening fast, sort of faster than you can respond to, particularly like when it's in the dark, it's overnight, it's in the wee hours of the morning in particular, so you've probably already been asleep for a while. It presents an extremely dangerous situation, and this is something that we see in a variety of locations in the United States, and the vast majority of them actually have the background geologic characteristics that we just talked about here, which are flat-lying sedimentary geology. Frequently, there's thin rock layering involved with that, and there's often, not always, but often a pretty significant clay component in the soil that comes from the rock because there's rock types like shale that themselves are already thinly layered and they produce clays in the soil. So there actually is a reason that a landscape like this is going to be very much poised to produce flash flooding, regardless of what the weather conditions or climate conditions have been in the months or years before the event. And as I already said, you put a foot of rain on a place, expect to see, a catastrophic outcome. But a landscape that's set up like the one you're looking at here, as we saw yesterday, and this situation is still unfolding. Hopefully, there's going to be rescues. There's still people missing here. I don't know, how long those efforts will continue before they direct more towards what you would think of as type of recovery type of situation. And frequently, a flood in a landscape like this that's been dry has a tremendous amount of debris in it because woody debris will collect in the channels during the dry periods when there's no water to carry it away. And you get a big punch of rain like this. And not only do you have flood waters, they're absolutely choked with woody debris from trees, and then more materials accumulated from structures that wash away, and it ends up becoming more than just a very fast moving water flood. So bearing all this in mind, this is the most recent of these events, but it was just a few weeks ago that you were seeing events similar to this in West Virginia almost day to day. They just had weather conditions in place that were causing thunderstorms to drop several inches of rain in one place very quickly. And it was producing flash flooding that was comparable. This is more severe, probably because of that sort of baked condition of the ground that made the runoff even more extreme. The rainfall totals here in Texas are probably greater, but the rainfall rates in West Virginia would have been very similar to what you see here, and of course, with equally catastrophic outcomes. So if you were to go onto Google Maps, and just take screenshots of landscapes in West Virginia or in Kentucky or in the hill country of Texas, you would note pretty quickly that they have sort of a similar sort of grain or character. I'll need to move the window here just a little bit. I'm going to zoom this back out. But up there in the top right, you got Eastern Kentucky. So that was an area that flooded very severely back in 2022. Over on the right side of the screen there, got the Fairmont, West Virginia area, got the Wheeling area here on the left, with Wheeling itself over there against the Ohio River, and then up in the top left you've got Kerr County, Texas. So the West Virginia and Kentucky examples, they have, need to use a better color. they have very, very similar topography because the background geology there is almost exactly the same. This is sandstone and shale of the Appalachian Plateau. What you deal with there in the Texas Hill Country, flat-lying layers, I think there's a considerable limestone presence there. I am by no means any kind of expert on the background geology other than the structural characteristics that you can see that contribute to that elevated drainage density. And all of these images are taken at the same scale. So the style of landscape is similar, but the actual physical size of the stream channels is different between these locations because they are different geologies in terms of rock type, and they do have very different climates as well. So let's clear out those drawings there. We'll actually zoom in here just a little bit to the top left. And even though again the physical scale of the drainages there in Texas is different, you can see in some areas, particularly like the ones in the middle of the screen right there, that a small stream kind of going up the hill will have 6 or 8 or 10 small branches going off of it. A branch of a stream there might just be several hundred feet, 1,000 feet long, or something like that. But essentially, all parts of the landscape are sloped, and when they're sloped pretty steeply. They go straight to a channel, and you've got that hard baked surface. Even though the elevation and the topography there is a little bit lower than what you see in Kentucky and West Virginia, you're going to be looking at a similar type of a flood response. So absolutely, there is a connection between landscape style and how a landscape is going to act if you put a tremendous amount of precipitation on it. And to kind of lay this out in sort of a comparison kind of thing, of one valley set that's going to be really steep and tight there on the left, and sort of a broader, more rolling one there on the right. So let's make two different style landscapes here. So the one that I'm drawing right now on the right, for geologic reasons, it's going to have a fairly low drainage density. So it's going to have rock types and soil types that favor the development of a smaller number of kind of larger stream channels on the surface. And then over here on the left, we're going to set ourselves up with something like we're seeing in these high drainage density landscapes, where one big stream here is going to have sort of a countless number of little forks and branches coming off of it, such that literally all parts of the landscape are either a channel or a steep slope. And you can take this in all directions. You sort of want the forks to have their own forks, and then those smaller forks have their own forks, and so on and so forth, until there's actually a tremendous amount of stream mileage in this landscape. I'm going to finish the one on the left there up. Going to run it in fast forward here just to keep things on pace. But when it's all said and done, we'll actually draw blue lines. So we'll actually draw streamlines on this just so you can get a sense of how all this would compare. And absolutely, this exercise is something that geologists do when they're studying flooding. Geology and weather interact quite a bit. Geology can produce weather in terms of how mountain ranges are set up. And weather also interacts with geology in terms of how the landscape looks and how water runs off the landscape to carry sediment away. So the two disciplines don't always overlap as much as they should, but they absolutely have a great deal in common. And there's a tremendous amount of interplay between the geologic characteristics like we're looking at here and more immediate sort of short-term weather effects like we've been seeing this summer. So we'll get this rolling here. Bear with me, and we'll talk about what the stream networks actually look like. So hang on just a minute. Okay, so two vastly different landscapes here. we were to kind of draw out a stream network on this one, sort of a limited number of possibilities here. And again, this is going to be an expression actually of what's under the ground there, what kind of soil it makes, how easily the rock is eroded, how easily precipitation can soak into the soil derived from the rock, all kinds of questions. In our high drainage density landscape here, we're about to be drawing for quite a while because the sheer quantity of channel length in this landscape is just really exceptional. Totally different ball game from what we got there on the right. And if you can imagine, if a raindrop falls in the area that I'm drawing right now, really regardless of where it falls, it's going to fall on a steeply sloping part of the landscape, and it's immediately going to be in a channel making its way downhill towards another stream channel, which is going to be met by even more runoff, and you can kind of take it from there. So a landscape like the one we just filled in there, that's going to flood hard and fast regardless. You could in fact take the same storm and sit it over top of everything I just drew right there. And the flood that you're going to get on the right side of the screen there is going to still move a huge amount of runoff, but it's not going to do it as quickly and as violently as the one on the left there. And to take this a step further, frequently in these high drainage density landscapes, the channels are really cut down into the land like you see here, and that leaves people sort of living along the rivers. They tend to be really cool, pretty rivers. A lot of times they're rocky, they have kind of bluffs or cliffs along the side of them. So they're appealing places to be. The problem with that is that you're of course in harm's way very much if there is a big flood event. Your choices for living in a landscape like this are either kind of up here along the hilltops, which is something that you see around Wheeling in particular, or down here in the valleys where the flood risk is quite extreme. Most of the kind of the sloped areas like this are just they're too steep to really use for anything in terms of building or something like that. So yes, geology and its expression in the landscape absolutely dictates how the landscape is going to respond to weather. What I drew in there is just that idea of the flat lying layering that's going to give you a scenario like the one illustrated there. And we would have to have some kind of big geologic boundary here, and on this other side we might have metamorphic rocks over here that are intensely folded. Their mineral content's really different, and they just make an entirely different landscape, right? So when you see a pattern like the one on the left there, which of course is the type of pattern that you see here in Kerr County in Texas, even really zoomed out like this, you see it again making your way back over here into the Appalachian Plateau. It's really at its most extreme globally here in Eastern Kentucky and West Virginia. I've said it in other videos. I promise you there are landscapes similar to this. There is really not anything quite like this anywhere on planet Earth. It's almost dizzying to look at. Of course, traveling in a landscape like this is challenging, but with all of that slope there and that many stream channels, this one's built to flash flood, just like what you see further north, up in Wheeling, or to the southeast of Wheeling in Fairmont, where there was a building collapse related to the flooding that got a lot of coverage over the past several weeks as well. So this is oh, this is not something maybe that you think about every day. You're probably not going to see it expressed this way in news broadcasts. There is mention of the hard baked ground for sure in Texas, but this idea of high drainage density, like how many stream channels are there in the land to take falling precipitation and put it in a bigger channel really fast. that high drainage density, along with other details like how the stream networks branch and things like that, these all impact how the landscape floods. But you can be sure that it's not at all a coincidence that so many of these big flash flood stories from the past few years and just from this summer alone are happening in landscapes that actually look very similar, even though they're in different parts of the country. We can probably take ourselves up here with the national map. This is an incredible tool to be able to see LiDAR like this, sort of on demand. I'll tell you what, and to see it in 3D that in the way that you now can, it's really something else. I say we'll let this fly us up to Wheeling real fast. All right, there we go. And if we zoom in on this landscape, actually be able to see some characteristics that are going to look a fair bit like what you saw there in Texas. And you have to take it a step further to get there we go. So that's the full high quality 1 meter scale LiDAR right there. And right away, you see that same sort of layered texture doesn't look unlike what you have down there in Texas. And yes, there's a good reason that you're seeing that, that similarity between these events. I would be interested to know, and I don't know this, I'd be interested to know how much details like what I've talked about here, drainage density, the way stream networks are laid out, the nature of soil. I'd be interested to know how that factors into flood modeling in landscapes like this. Obviously, you want to look at flood history. You want to look at how river gauges behave with a given rain event, but certainly landscapes like this absolutely have a different behavior, a different tendency than the one I'm in, for example, in the Appalachian Piedmont. We don't have anything like this topographically. We don't have geology like this. And if we were to catch a rain event like the one we're talking about here, you would see tremendous flooding, but you would not see the human toll, and you would not see the level of damage from it for reasons of how the land is used, how the land is developed, and the simple fact that you're going to have a little bit more time to warn people and to actually get people out of harm's way. So, hope this video was useful. Talked a lot about weather and geology with Helene, of course, and just like weather interacting with topography, forcing extreme rainfall in certain locations, certain geologic scenarios being more prone to landsliding, for example. Certain geologic scenarios, like the one we're looking at here, are absolutely different in terms of their flood behavior. And we've seen a lot of that. And as long as you have these convective thunderstorms that produce rainfall at inches per hour, you always run the risk of seeing it again. And even if you know it's coming, it's likely to happen fast enough that getting out of harm's way, particularly if it's at night, is going to be extremely challenging. So I hope this video was useful to you, and I hope you check out the next one when it comes along.